Okay, so welcome everybody to what is the last lecture of this course. So congratulations to everybody who's hung on until the end. There are some issues with the homework. There is something that we need to do about getting homework 3, 4, and 5 out. I understand your impatience. Working on it. Yes. Okay. Good. Now, the content of this lecture here is not going to come up in the exam, so don't worry about it. Okay, so if you're just here to make sure that you have to, know something for the exam, okay, you can basically relax, and this lecture will not show up. And yeah, so okay, I'm going to turn around. If anybody wants to walk out, I'm not going to. Okay. Now, for the next 2 lectures, though, you'll be doing the lecturing and I'll sit here. And we have a fair number of projects. So we have 22 where I got an email. And I think there might be some more missing who didn't send an email to me with title and abstract. So I sent an email with a link to a Google Doc to the news group. And this one is world editable. So bear in mind, this is world editable. In other words, you can screw it up badly for other people if you want to. I trust that you don't. I have a copy of it, but you're making life hard for everybody else if you screw it up. Okay, so there, check that your name is on the list. If it's not on the list, send me an email ASAP. Because if you're not on that list, you will not be giving a presentation. Right? Good. Secondly, it would be awesome if you could link, or as in post a link, to where your presentation is there. The reason is each of you has 5 minutes to give a talk, so you get 5 slides maximum, no exceptions. And if we spend 2 minutes in each case to just plug and replug the laptop, it'll take a lot longer. Okay. So this is why preferably we should try to get everything onto my laptop, and we'll run it from my laptop. Okay. There are some cases where this doesn't work, and I'm happy to use somebody else's laptop, but let's squeeze out time where we can. So you have 5 minutes and probably time for 1 to 2 questions. It's also good practice for conferences. Good. Yeah, there's the exam. We'll use the solutions are out as of this morning. They are posted on the news group. They'll go up on the website shortly. And okay, so that's about what I have to say for this. Now, in terms of content, yeah, we didn't cover all the curriculum. That's because we slowed down. We slowed down a lot. There will be probably some reorganization in terms of curriculum for the next semesters, because there's clearly some discrepancy between what we should be covering and what is possible to cover in a given time. Okay. Now, the thing that I want to show you today is a rather useful technique, and it's enough if you just get the spirit and the intuition of it. I'll be walking you through a few proofs, and I'm sorry, I'll be violating the many equations per minute rule. You can, look over the equations later on again if you want to, and if you don't want to, don't worry. Okay.
Before going to the lecture, I want to know, for the final exam, do you have the trend that you had in the midterm exam, or should we go through the final exam from the previous years?
Okay. So, will looking at previous exams help you for this exam? Well, in general, yes, of course. However, there's clearly covariate shift because each lecturer does things a little bit differently. The point is, we will not ask for anything that we didn't cover, right? No, we didn't cover everything. We didn't cover a lot of stuff, and I'll show you in the end what we didn't cover. Now, obviously, the emphasis will be on stuff that happened after the midterm, but it doesn't mean that you should forget about what a perceptron is, right? So in other words, do remember what happened before the midterm, but obviously there will be more questions about the second half than about the first half. But if you hear some rumors about topic X is going to appear or topic X is not going to appear, this is bullshit. So don't fall for it. So don't fall for something like we will not ask learning theory, right? I think that rumor went around last time, and some people chose not to prepare for learning theory. I only found out about the rumor afterwards, otherwise I would have probably reduced the amount of learning theory not to screw you, but basically don't fall for rumors, don't. Okay, so the exam will be such that, again, probably you won't be able to answer all the questions in the given time. That is a good thing, because it means that nobody, unless you're walking on water, can answer them all in the given time, so you can choose the ones that you will have less trouble answering. Okay.
Isn't the exam 3 hours?
Yes, 3 hours.
Yes. Well, there will be more questions. You can bring anything that's on paper. You will not use anything that's electric, and don't use your cell phone, your iPad, or anything else that requires electricity for the exam. So just don't do it, because you'll walk out of the exam immediately as if you do that. Okay. So leave your cell phone in your bag, turn it off, don't touch it. Okay, good.
Sorry,
Yes?
I would ask the same question again. Are going through the past exams would help us to get prepared because the midterm is done? So I wonder if the final is going to be similar to past exams.
So my guess is probably looking at the homeworks will help you. Looking at the slides will help you. Right? Looking at the at other exams, well, will help you overall become better with machine learning. But we will not take old exams and recycle them, if that's what you're asking. We might by accident happen to recycle it, but it's not our intention. Okay, good. So with that, let's get started with multiplicative updates. So this is going to be a slightly different thing from what we've done in the past, and it, however, actually ties rather nicely to, well, a couple of things that you might have done before. So I don't know whether you read XKCD, but if you do, you would have probably seen this, right? This is about how would you go and find an expert. Right, so enjoy the slide. But in general, let's say okay, I understand nothing about baseball, but some of you guys in the room here probably do. But foolishly, I've decided to bet on baseball, so I'm going to ask each of you each week, who's going to win. And I'm going to use this to, determine my betting strategy. And so the question is now, how can I design an algorithm such that in the end, I'll do as well as the best of you guys here in the room? As in, do as well as the best of you guys here in the room with the benefit of hindsight. Because while some of you might clearly think they know a lot about baseball, you'll only know after the season, who really knows the stuff best. And my goal is, by just asking you each week to find out, who I should, rely on. So let's formalize that a little bit. So have a pool of experts. And, well, and each expert makes a prediction, FIT, or FET. So at time t, expert I makes a prediction, and we observe YT. And we want to use this to find out, who we should trust. And not just do we want to identify this guy, we also want to do well while we are trying to find out who this guy is. And the simplest thing you could think of is the halving algorithm, which will work really well if I can assume that there's at least one guy in the room who really gets everything right. Okay, so let's start with our pool of experts. There's a pool. And while I ask them, who will win the next game. And, some get it wrong, so I discard them. So now I have a smaller pool. And next time I come along and ask them again, smaller pool yet. And so basically each time I just, get rid of all the experts in the pool who don't do well. Okay, so another one. Okay. And then who of the two is it going to be? Well, okay, she gets it right. So what I've just shown you here in pictures is the halving algorithm, which is basically at each step, find out who gets it right, send all the experts home who don't do so well. Okay, so here's the algorithm again. So, pool of experts, discard whoever screws up. And so you can easily see that this algorithm, if I have a pool of experts of size E, makes at most log base 2e errors. Because we will only get it wrong if the majority of the experts gets it wrong. However, if the majority of the experts gets it wrong, that means that next time the majority of the experts will die. Right? So therefore, quite clearly, after log base 2 of e errors, I'm done. So this is awesome if we have somebody in the room who's a natural at baseball and who will get everything right. My guess is probably none of you are quite that good. I don't know, maybe some of you are, but I'm definitely not. So what happens if, experts can make mistakes? So you shouldn't really fire them immediately because maybe, some experts, you want to still find the one who makes the least number of mistakes. So can we still do something that works very similar to what I described? So if you think about it, what really went badly wrong in the beginning is that we just sent home all the experts who made a mistake, even just once. And, well, so the idea is maybe we shouldn't quite send them home, but maybe we should listen to them a little bit later. And I'll show you exactly how that works. So the quantity that we're interested in is twofold. One is the loss. So this is basically, how many betting mistakes or whatever I make. And the other one is the regret, which is basically how well do I do with a given strategy relative to the best expert. So basically, if all of us here in the room are really awful at predicting baseball, well, my regret might actually be very small if I pick a random guy here, because, well, we all stink. However, if there's one guy in the room who gets it really right, then my regret will be very big because I could have done so much better by just, hiring this guy. So bear in mind that our predictions need not match any of the experts directly. So we're basically creating a meta-expert by taking all the expert predictions and compiling it and using that to come up with, something on our own. Okay. So here's what you do. Okay, let's start again with a pool of experts. And now if they screw up, well, okay, we listen to them less. So we multiply their weight by, some small number. And then, we get another case. And so now you would see that there are some parts that are a little bit more shaded. And so the different shades of white here will tell you how much you should trust those experts. Here's another one. And so, those who get a lot of things wrong, I will trust them even less, and so on, and so on, and so on. So now what you have is that I'm still listening to all the experts up here on the upper right, but I'm just not listening to them very much. Whereas those get it kind of right most of the time, and I will listen to them a lot. So in other words, I'm now weighing my pool of experts based on the loss, or the damage or whatever they caused, or the profit, or the money that they made me over the past. Does anybody have any questions about the intuition of the algorithm? So if you're curious about it, this is apparently some swimming pool in China. And the description below that is about the water quality. Okay, good, but we don't care about the water quality. So, weighted majority. Here's what we do. In the simplest case, and we'll build it up and we'll get more and more complicated algorithm as we go along. So let's say we just have a binary loss, like player wins, player doesn't win. And initially all the experts have some initial weight, some W is 0. You might just give them all a weight of 1. You don't have to if you know that, well, probably those guys up there, well, I really don't trust them, whereas the ones over there, they look like they really know it, right? So I can give them a higher weight to begin with. And I use a weighted majority to make a prediction. So this will come in handy later on if we use regression, because then I don't take the sign, but I just take that weighted average. And I'm going to observe the outcome. And then these experts that get it wrong will be multiplied by beta. Beta is a number less than 1. So that's exactly what we saw before with the pool, where things got shaded with more and more layers of white, which is kind of nice. We can do that nicely with opacity, but think of this as your function class. And so there are actually two things that I can do. One is to draw based on the majority. And the alternative is to, well, just take that pool of experts with a corresponding weighting and draw one of the experts from that pool. And actually the latter turns out sometimes to give you slightly better bounds. So now let's analyze this. And what you'll see is that it's the same type of analysis over and over again. You basically construct an upper and a lower bound. You put them together and you check what happens. So the lower bound is going to be based on the weight of a single expert. So, each expert, when you make some mistake, well, so we're here in the second last row, well, he gets downweighted. So therefore, after t steps, so the weight at step t plus 1 is W is 0, beta to the L et, so that's the loss that the expert incurred in that entire sequence. Now I'm defining Wt to be the sum of the weights of all the experts. So remember, this is unnormalized. And of course, the weight of a single expert has to be less than the sum of the weights of all the experts. Now, for the weight of all the experts, so this is similar to what we had before with our swimming pool, well, if the majority gets it wrong, then, we will downweight at least the majority. So therefore, the weight at step t plus 1 is less equal than half the weight at step t. That's at most the number of guys that I'm not downweighting, plus beta times 1/2 Wt. These are the guys that I'm shrinking. So in other words, Wt plus 1 is less equal than 1 plus beta over 2 L hat t. So that's basically the expected loss that I'm incurring in that sequence. Okay. So what you now have is you have a upper bound on Wt in terms of the expected loss on the sequence, and a lower bound for a single guy in terms of, well, the loss that a single expert incurs. So I can just chain those inequalities together. Let me do that. So remember, we have WET is, of course, nothing else than WE0 beta to the LET, which is less than WT plus 1, which in turn is less equal than 1 plus beta over 2 L hat T W0. Okay. So taking logs
We can't really see it.
times okay.
If you turn off the lights,
It's well,
the lights on the table, is that a button?
no, that's not going to help. So what the camera does is it tries to calibrate the brightness. So as soon as I put my hand here, it'll make it so that you can see my hand and not my handwriting. Notice it? Right. So there is very little I can do about this. Sorry. Okay. So then, yeah. Basically, what you have is you have this term here. You have this term here. So taking the log and using the fact that these betas and the 1 plus beta over 2 are obviously less than 1. So you get the negative sign. You will get that W, the log of WE0 plus LET log beta is less than log W0 plus L hat T log 1 plus beta over 2. Now, using the fact that these are negative numbers, and we need an inequality where this is upper bounded, right? So we just multiply by -1, everything flips. And if you then solve for L hat T, you get the equation down here. This is just algebra. Question?
I assume that for each time that the majority gets it wrong, right? Is that your assumption?
No.
But how would you get that equation? Like,
Okay. So no, basically whenever the majority doesn't get it wrong,
Yeah, that's what I think.
then, well, you know,
Then how would you apply
it's then it's no big deal. I mean, then, I mean, basically, this is about the most adversarial setting, where the majority, where basically the adversary always gives you an instance where the majority gets it wrong. If at some point you receive an instance where the majority gets it right, then, you know, all the wrong guys get shrunk even further. Right? So this is good for you, because then you're learning without paying the price for it. So these are about the most pessimistic worst case bounds that you can get, right? So, you know, if I wanted to be really nice to you, I would feed you all the simple observations in the beginning where the majority gets it right, but you're still correcting and updating. Because, you know, some of the experts get it wrong, and you basically find out all the experts that are no good without really paying any damage. And I'll wait with the really difficult observations until the very end. So I can probably find an ordering of the data where you will make no mistake whatsoever until the end. But since it's an upper bound on the number of, you know, loss, on the loss, you know, sure, I can find some ordering of the data in which you do much better than the upper bound. So this is a little bit different to the perceptron algorithm, where you basically need to make a mistake to learn. Here you can learn even if you don't make a mistake, but if only, let's say, you know, some of the observations in you will make a mistake. Some of the experts make a mistake. Right? So that's kind of nice about it. Okay, so here we have our inequality again, and I've just marked up in yellow the relevant pieces. So W0 is the weight of all the experts. So if I have any experts, that's log n. And And in this case, I might give each expert, weight 1, so the third term just goes away. And so what we have is basically that, our strategy will do no worse than the best expert times some number that's a little bit larger than 1, plus some additive constant. Okay. So now you can start thinking, what should I do? What should I do if I, play only a small number of rounds versus what should I do if I play a long number of rounds, right? So question, if I only play a very small number of, rounds, should I pick a very small beta or a very large beta? Who votes for a small beta?
Small, close to 0.
So yeah, small beta, basically beta close to 0, and large beta means something that's close to 1. So if I play a small number of rounds, who votes for small beta? Okay. Who votes for large beta? Okay. So the experts in my pool have to have an opinion. Here I have a lot of experts who don't have an opinion. Okay, let's try again. Small beta? Okay. Large beta? Okay. Okay, so we still have some experts without opinion, but the point is, yes, you want to have a small beta. Small beta means you are very quickly throwing out experts that perform poorly. So that's basically, if you are under time pressure and you need to very, very quickly come up with something that does reasonably well over that sequence, you need to zoom in on a good expert really, really rapidly. On the other hand, if you have a lot of time, then you actually have the luxury to wait a little bit longer and see whether maybe that best expert just happened to get really unlucky in the beginning. So you can cut him a lot more slack. So that's the difference between, for instance, whether you're sitting in an exam and you have 3 hours versus your PhD, right? If you're, in your PhD you have, 4 or 5 years, and you can screw up for a few hours, no big deal, right? I mean, nobody will even know it. If in the exam of 3 hours you screw up for a few hours, that's not a good strategy, right? So that gives you a bit of an intuition why an aggressive beta will very quickly zoom in on some experts, but it might not be a very good expert. So what really happens is we are exponentially fast actually converging to the best expert, right? Because if you think about it, we have this weight, right? So WET plus 1 is basically the original weight and then beta to the LET. So that's basically how that expert's performance. So if you have one stand-up guy, he will very quickly dominate everything else. And the algorithm tells you, well, okay, this way you'll very quickly find that guy. That's awesome, right? Well, it's kind of, okay, question?
Can their regret be negative?
You could have a negative, well, not the regret, but the loss. You could have a negative loss, but you could always then just add a constant to that loss and it would rescale everything. So the only thing you should not have is unbounded negative loss, right? Because that would be extremely weird. It would basically mean by solving one thing amazingly well, you could make up for all the things that you've gotten wrong in the past. So it's not like you can, so you don't have the equivalent of going to confession and everything is made good.
I guess my question is, by running this algorithm, do you have a chance to literally do better than expert which expect?
Okay. Now that is a very, very good question. Can I do better than the best expert? Can I find something that will do systematically better than the best expert in the pool? Well, not with this algorithm. And this is exactly the Achilles heel in these multiplicative experts approaches. So, for instance, if you use an algorithm like this for personalization, right, and you have a lot of keywords, and you treat each keyword as an expert, then you're very, very quickly going to identify that single keyword that personalizes for you best. But that may be a really horrible thing, because, I mean, you're probably interested in more than one thing. So it'll find, the most interesting singleton, but it will not give you a very good profile. And in practice, that's actually what happens if you use multiplicative update algorithms for instance, personalization. So they very quickly identify individual items, but if your best solution is actually one that is, let's say, a linear combination of those guys, they may do a rather poor job at it. The problem is if you want the latter, you will get slower rates of convergence. So remember when Banabas walked you through the 1 over square root sample size type of convergence analysis? That's what happens if you want to have linear combinations, for instance, or if you have a more complex function class. If you just want to find the best guy, that's a lot easier. But it also means, well, you'll just do as well as the best guy. Okay, that's a very good question. Any other questions here? Okay. So, how can we modify it further? Well, it's called essentially just a exponentiated gradient or multiplicative update algorithms. So if we don't have a 0 and 1 loss, we can actually still, use the same algorithm. So what we simply do is the weight gets multiplied by e to the minus eta times the loss that at expert occurs at time step t. And so you use exactly the same analysis again. So the lower bound is basically that the weight over all the experts is greater than the weight of any individual expert. And the big gun that we can use for this purpose is a variant of the Höfting bound that looks very unlike anything that you would have seen before. So I'm going to spare you the particular details, but basically you get a much faster rate of convergence. So what you'll get again is that you have performance as well as the best expert, and then you have some terms that you can actually show will go like 1 over square root t. Basically, you just set that step size to be 1 over square root 1 over square root t, and you're in good shape. So basically, your loss goes like the loss of this best expert plus a term that scales like square root number of steps that you've taken. So if you divide that by the number of steps, the average loss will basically go to the best thing that a single expert can do. And yeah, so that's what you get here. Any questions about that so far? So don't worry about the details of the proof, but essentially it's the same machinery again. You lower bound the singleton and you upper bound all of the guys. And then you just match those two bounds and you see what comes out. Right? That's basically what we had here. Any questions about that so far? Okay, good. So now let's use this for boosting. So one of the reasons why I've walked you through that experts framework is because this is a very nice hammer that we can use over and over. And the various applications that I'm going to use it for is boosting. I'll use it for games, as in game theory. And third, I'll use it to draw a few connections to particle filters. And I'm not going to walk you in detail through AdaBoost. I'll just show you what is different from what I'm doing here in AdaBoost. And then, because that would be quite comfortably a lecture in its own right. So what's the idea about boosting? Well, the idea is I have some data set x and y of xi and yi, and I have some weak learners. So I have some learning algorithm that's not so amazing, but it does something that's better than random. And more to the point, I can actually design it in such a way that for any weighted distribution, of observations, the performance is, better than random by some gamma. Performing as well or as poorly as random would mean that that weighted combination of yi f of xi is, well, basically 1/2. Sorry, there's a small typo because I would want to have variables that go between 0 and 1. So I basically have, 1/2, 1 plus yi xi, f of xi, but okay, sorry about that typo. But the idea is then, I want to actually combine those weak learners to get a stronger learner. And so the question is, how do we do this? How should we weigh the instances? And the idea is essentially, I want to find a distribution over observations that is hard. And so if I always give it exactly a distribution of observations where, the algorithm so far has performed poorly on, it will focus on those. And now the experts will be individual functions that I'm drawing out of it, so it's kind of a back to front setting. Okay, so we are now weighting the data, and then we get an expert in each case, a function in each case. Okay. Any questions about that so far? So this is, well, imagine it's like I'm teaching this class, and I give you all the material and look at your homework, and then I decide, well, okay, you didn't do so well on that, and that, so let me give you more of that homework. And then, I notice you're still having trouble with a small set of things, and I give you those more. So when you learn a foreign language, you often do that, right? So you basically have a stack of, words with, the matching word in the foreign language, and you go through that stack. And whenever you get the word right many times, you put it away, and you keep on focusing on those words that you don't know very well so far. That's effectively the idea here. And so all you have to do is better than random, and overall you'll eventually learn things. Okay. So this is the non-adaptive version of boosting. It's non-adaptive because basically we will not take the performance of the system into account to gauge whether I should trust that particular function more or less. Okay, so basically I go and start with maybe a uniform weighting of the observations initially, and then I find a weak learner which does better than random on my data set. And I'm assuming that those f of xi's are bounded between 1 and -1, so things are okay. And so then I go and reweight the instances as follows. Those where I performed poorly, I keep their weight. Those where I did well on, I will decrease their weight. So that's basically this reweighting step here. And in the end, I'll give you back a linear combination of the f's that I've found so far, and my claim is that this is doing something sensible. Any questions so far? Yep.
Are we using like multiple learning algorithms?
Well, your weak learner could be a combination of 50 algorithms, but for me it's a black box. And all I send to the weak learner is, by the way, here's a weighted set of observations, give me a solution back. So if that black box contains 20 smaller black boxes inside, and there's a chipmunk deciding which one to pick, I'm perfectly happy. I don't care. As long as out of my big black box, I get a function back. So some of the things that you could boost over are, for instance, decision trees, neural networks. You could take a genetic neurofuzzy algorithm if you really wanted to. The math would still go through. So the math doesn't care about how you get that weak learner. The only thing you care about is that it gives you something that is better than random. Okay, so let's see how we can analyze this. So if I have a mistake after those t steps, it means that that the majority of the functions in my set must have gotten things wrong there. So that means that the weight WIT for basically for observation I has to be greater than e to the minus alpha t over 2, because it would have gotten more than t over 2 of the functions wrong. So therefore I know that the lower bound on the aggregate weight, so remember it's exactly the same trick again, the only twist is that now we count all the guys where we screw up, is greater or equal than the number of errors that I make times e to the minus alpha t over 2. Right? Now let's also compute an upper bound. Well, the upper bound is basically just, the sum over the previous weights times how much I downweight them. Now I can go and renormalize and use this Höfting bound from before again. And you can check that this is basically going to be, since this is now the average performance, it has to be, at least gamma better than random. So we have gamma plus 1/2. And since, I give, take a step size of size alpha, and I do that t steps, I have alpha times t times gamma plus 1/2. That's the good part. But we also pay a price, so this was what occurred in Höfting, so it's t alpha squared over 8. So now we have an upper bound, we have a lower bound. We combine those two as before, and then, it means that the number of errors is less equal than, number of observations times e to the minus t gamma squared for alpha equals 4 gamma. It's kind of nice. So in other words, the probability of making an error goes to 0 exponentially fast, provided that you have a weak learner that's at least as good as gamma at each step. Okay. Is this the smartest thing you could do? Probably not. Because if, let's say, at some point you encounter a really, really good solution from your weak learner that pretty much solves everything, you should give this guy a really high weight. And if by some, accident I get something that's very poor, you should give it a small weight. Furthermore, it means that you have to know gamma beforehand. And that is really tricky, because we don't. And that's where AdaBoost comes in. So that's Freund and Shapir, and yeah, this is probably one of the really big papers. Basically, what you do is you take the weighted error for the observations, and you give it a step size. You take a step size of not alpha, but you make a step size, 1/2 log 1 minus epsilon over epsilon. The specifics come from you're basically performing gradient descent in function space, and that would be quite a lengthy type of analysis. And you also use this as the weight for the particular weak learner that you've generated. The cool thing about this is now we don't need gamma anymore. We will do well regardless. Okay. Any question about that? So the algorithm is really simple. It's basically just, reweight your observations. You do it exactly as you would have done before. Just that the step size is now variable. And yeah, you basically get a significant prize for that if you come up with this algorithm. Any questions? Right. So, but you've seen it works very similarly to the multiplicative update algorithms, except that now we perform multiplications on the observations rather than the functions. So what can you use it for? Well, you take linear threshold functions, decision trees, stumps, neural networks, and it works quite nicely for all of them. So you could think, well, hey, this is nice, well, why don't we use it with an SVM? Right? After all, SVMs are good for you, so why not support vector machines? However, actually there's a very nice piece of analysis by Rob Shapir et al. So I've attached a link to that, and that's probably the convergence analysis you want to look at if you care. they showed that boosting actually already gives you a large margin classifier. So what that means is that one of the reasons why boosting will not overfit so much is it doesn't just give you any odd solution, it gives you a solution that separates the data really well. So it's this nice boosting the margin paper. And so if you have a large margin classifier and you want to build a large margin classifier out of large margin classifiers, it's kind of pointless, you get the same thing as before. That's why boosting SVMs is not such a bright idea. Okay. Keep in mind you can actually overfit. And it's kind of funny because initially all the papers on boosting were written along the lines of boosting will never overfit. Yeah, because they trained it on very clean data sets. As soon as you have very noisy data sets, boosting will overfit just like any other algorithm. One way to avoid that is by either stopping early or by limiting the weight that single observations can have. And if you do the latter, you get an algorithm that is boosting resistant. Yeah, the name is robust, as in robust, right? And that does exactly that. So basically, you do your multiplicative updates, but you never give any single observation a weight that exceeds some limit. Okay. So this was boosting. Any questions? So to recap, basically, take an initial uniform weighting, downweight those observations where we get things right, either with a fixed step size in the context of non-adaptive boosting, or with an adaptive step size that depends on how well you did overall in the case of ADA boost. That's it. So who's done game theory? Okay, that's actually a reasonable number of people here. But I guess you've all played this game, right? So what's going on here, right? So I basically can take 3 different actions, and well, if I play with somebody, my opponent can also take 3 different actions, and then depending on, you know, which combination I pick, I'll win or the opponent will win. The fact that either I win or the opponent wins, and that we gain or lose just the opposite of each other, makes this what's called a zero-sum game. So a zero-sum game is a game of the form, my gain is your loss, and vice versa. Okay. Now, I don't know if you've ever played, you know, rock, scissors, paper with a kid, especially when they're little. They'll always, let's say, play rock. They'll always play scissors, right? And if your opponent does that, it's really easy to beat them, right? So in other words, if you play a pure strategy, which is basically one single action, then your opponent can usually screw you rather badly. So don't do it. And this is effectively what will now become more formalized, and it'll give us, you know, all the nice things about Nash equilibria and so on. Okay. So by the way, this is the payoff matrix here. And we'll be dealing with matrices of that form for the next maybe 5 minutes or so, maybe 10 minutes. So the Nash equilibrium is one where both players have a strategy which might, you know, give a single action, or, you know, might imply a distribution over actions, such that none of the players has an incentive to change their strategy given the choice of the other party. So it's basically a saddle point. Okay, that's a Nash equilibrium. So now there's this von Neumann minimax theorem. And it says that, well, basically the policy for the row and basically, you know, the payoffs for, you know, if you view it from the viewpoint of the row player or for the column player, it's the same thing. So in other words, my payoff matrix M is such that if I perform the maximum over j for each particular x, so that's basically, x is my mixed strategy, and the player in charge of j, picks the best thing he can do. Or likewise, if I pick the best thing I can do given a distribution over actions from the player that played j, then those two values match up. And the proof is actually very simple if you use linear programming. So the first thing to notice is that, well, if I pick the maximum over all the vertices, I might actually take the entire convex hull and it gives me the same value, right? That's just because if I have, it's a very simple picture, this is my polyhedral simplex, then if this is the direction of the objective, then finding the optimal solution is a vertex solution regardless anyway. So whether I optimize just over those 3 points or over the entire set makes no difference to the optimization problem. Okay? So therefore, I can switch the max for a maximum over a polyhedral set. Okay? So then I apply just standard linear programming duality, and I get that the max and the min and the min and the max, they're dual to each other. Then you apply the vertex property again and you're done. Okay. This is a proof without really doing any work, by using linear programming underneath. You can prove it directly, and that's a lot more work, but you can basically rely on linear programming. Okay. It's kind of nice and it's a useful. Yep.
So X is a strategy. What is M and Y here?
So M is the payoff matrix. X is the strategy of the role player, and Y is the strategy. Sorry, the column player, and Y is the strategy of the role player. So basically, X is your distribution over rock, scissors, and paper. Y is my distribution over rock, scissors, and paper. And so what I can do is I can come up with the optimal thing to do. Suppose you are forced to play from your strategy and keep it fixed. Then I can take the single best action for all of those things. Likewise, you could do that if my policy were fixed, you could pick the single best thing. And what it means for the Nash equilibrium is that we both have policy distributions such that there's no benefit for us to change anything. Mind you, if you play rock, scissors, paper, and you really can't catch anything off, when the other guy is going to respond, the best thing you can do is uniform. Anything else will make you lose something. So basically, if I draw my decision on a piece of paper, put it down, you do the same thing, then in the end we open both envelopes and we find out that's the type of scenario. Yep?
I'm confused that, is this X like randomized strategy?
So X is a distribution, yes. So X is basically a probability vector. So the entries in X sum up to 1, they are greater or equal than 0. So that's basically my probability simplex here. So this would be, for instance, distribution 1, 0, 0. That would be a distribution 0, 1, 0. And here it's 0, 0, 1. Right? Anything in here is a linear combination thereof. I mean, what really happens is here's the origin arrived, and then you're just staring down on that probability simplex. So it's like you have those 3 sides, you draw the simplex, and that's really where all the interesting things are happening. Okay, so the question is, can we find such a Nash equilibrium efficiently, approximately? And there's a very simple game how you can do this. So I'm going to show you the protocol, how you get there, and then we'll prove nice properties about it. So basically what I'm going to do is I'm going to start with some initial, maybe uniform distribution over all my actions that I could take. And for t rounds, I do the following thing. The opponent picks the best distribution qt plus 1 using my current policy, pt. And then I look at how well I would have done in this context and reweight my policy. So I get the next policy with weights, pi t plus 1. Sorry, there's a typo, it's not t plus t obviously. And it's essentially e to the minus eta times, the sum over all those regrets that I would have incurred by doing things. And then, well, obviously, if you think about it, this gives me a weighting, so I know that the regret bound tells me that, the losses that I incurred is less than, the single best thing that I could have done, plus, and then you have something that goes like order 1 over square root number of steps. So that's exactly the multiplicative updates guarantee that we had before. I'm just using it in a completely different way here, but it's the same math. Okay. So to recap, what I'm basically doing is I'm getting a sequence of probability distributions, and I know that if I play that particular protocol, the average payoffs that I would have had are less equal than the best single payoff that I could have had based on that sequence of policies of my opponent plus some small term. So there we go. So that's basically the first inequality in the top line. Now if you think about it, taking the minimum over the best policy, or doing again the optimization over the probability simplex, doesn't make any difference because of that picture here. So we get an equality in the last line. However, since we basically designed our algorithm such that the opponent will always pick the best distribution, right? So first of all, if I don't take the minimum over p, then the average over some p toss is going to give me something that's less equal than picking the best thing I can do, right? So that's the first inequality, the green to the red block. Now that red block, I can again bound by picking a better strategy qt rather than an overall optimal strategy. Right? So that gives me an inequality chain that goes from the green to the yellow bit. So first step is you basically realize, well, if I don't do the optimal thing, it can only get worse. And then secondly, if I do something that is specifically targeted at each step, again I can only my inequality can only get higher. Now the yellow block is exactly what we had in our regret bound, right? So what I can therefore do is I can chain things together, right? So we get that red bit here is less equal than, and now what we have here is basically, okay, I should have colored this accordingly. The minimum over p, sum over all those q's, I can only get better if I replace that last bit here by the maximum over q. Right? It's this bit here, so I should have colored it a bit differently. And so, but that's exactly what we know is also the value of the game, right? This was what we have here. So in other words, what we can see now is that our average strategy, right? This is basically the best the opponent can do overall. And this is our suggestion of our strategy that we should be playing. It's not going to be much worse than the best thing we could have done, plus a small term here. And that's exactly the guarantee we need. Mind you, you can make things a little bit simpler, because the best thing for the opponent to do is just pick that single action where you're screwed the most. And that now makes for a very simple algorithm, right? Basically, I design, a policy. You pick the single thing that hurts me the most. I then go and reweight my policy. And again, you pick the single thing that hurts me the most. And that's going to give me very fast convergence to something that's nearly optimal. Yep?
So when both of the opponents they take action at the same time.
So okay, so what I've described here is a scenario which will help me to find the optimal, the optimal policy. So this is, how to, by training, by playing the game, find the optimal thing. Now, if the opponent doesn't, do the optimal thing for him, so the opponent might also have his own distribution, then you're actually getting into an area called Bayesian game theory. Okay. So you've probably sometimes played chess with a guy where you know that he was really weak, right? Or some strategy game against somebody where you know he's really weak. So in that case, you might not necessarily do the thing that is minimax optimal, right? So you'll play differently rather than against the player where you know that he's very strong. You might do something that's super risky and that a smarter player could completely, destroy you if he figured it out. But against the weaker player where you know that he may not actually be all that good, he might not actually discover, the weakness in your move, you will be able to do better. So what I've shown you is the algorithm where you will be minimax optimal against, the very best opponent that you can find. If you have an opponent that is not perfect, you can do better. So it's quite fun because those things occur, for instance, on the internet when you do computational advertising. Then if you have additional side information and other things, you might actually have arbitrage. So you can make money by basically buying ad space low and reselling it high. And yeah, that's where game theory comes in again. It's a good question. Yep?
So the solution to this game is just the solution to the linear program that we saw in
Correct.
right? So why don't we just solve that and use that strategy every turn?
You could do that. That's perfectly reasonable, but this may cost you more time than the algorithm that I just showed you, which is very simple.
Okay.
So this is basically a very quick and dirty way of solving a linear program. I could have just set that entire thing up as, hey, here's a fast way of approximately solving linear programs.
Yeah.
And then most of you would have just started yawning rather loudly. That's why I set it up as a game. On top of that, this way I managed to show you a bit of game theory. But you're spot on. And there's this nice connection between game theory, convex programming, optimization, multiplicative update algorithms. And yeah, that would be a really fun class in its own. Okay, that's a cool question. Any other questions? Okay, so I'll conclude with going back to something that Barnabas covered a bit, particle filtering. So remember sequential Monte Carlo, right? And I'm just really super simplifying things. And this might also explain to you a little bit why multiplicative updates are sometimes a blessing, or let's say rather they can be a curse in disguise, not a blessing in disguise. So remember in particle filtering, well, you basically observe a data in a sequence, and at each step, well, you want to basically approximate this distribution, P of theta given x1 to n. Or at least you would like to have draws from it. So if there's just one parameter theta, we can just draw maybe 1,000 of them to begin with. Then we just apply Bayes' rule, because P of theta given x1 through xn is just proportional to P of xn plus 1 given theta and x1 to n times P of theta given x1 to n. So in other words, the term that changes is that second term. And that's what we would have to use to downweight the observations. So in other words, our weight for a particular particle which corresponds to a particular choice of theta is just take the original particle, multiply it by how well it fits, the next observation. So under the assumption of conditional independence, so this is really a caricature simplified solution, well, you have a very simple algorithm. The algorithm is start with some random guesses of what your solution should be like and downweight them as you go along. Well, that's a really stupid optimization algorithm, right? Because you need a lot of parameters to begin with, you try them all out, and very quickly you will find out that most of them are garbage. That's about as bad as genetic algorithms. Yep?
What happens if your initial samples are like bad approximate to your optimal?
Yes.
Are you going to find it?
So if my initial sample is bad, then I'm screwed. And that's exactly the problem with multiplicative update algorithms with experts. If you have no good expert among your set, you're stuffed. Now this is a problem. I mean, if you have to solve a real problem and you invite a panel of experts and you find out, well, maybe you need a very specific subject area and you send all the other experts home, you're stuck with one expert. What you do in practice then is, well, you invite more experts of that one kind. And then you find again the best expert among those, and you keep on zooming in further and further until you found where you are. And this is super ineffective if you use multiplicative experts, because you need all those large number of experts to begin with, and then you just start sending them home, so you pay the huge outlay in the beginning. Okay. So what would you do for sequential Monte Carlo? Well, so first of all, what you'll see is that the loss for multiplicative updates corresponds exactly to the negative log likelihood. That's what we want to minimize there. The weights are the weights. For experts, convergence is good news, and we can say, hey, we've converged, we solved our problem. For particle filters, this is about the worst thing that can happen to us, because it tells us, well, there's only one sample left and everything else is garbage. Okay. So what you have to do there is you need to resample to essentially, refine the estimate around that solution. And that way you can adaptively zoom in and refine. Okay. So let me show you a slightly less stupid example, namely sequential Monte Carlo on a chain. So basically, let's say we have some parameters here that are latent. Okay, we have some guys that are observed. And here we have, these are maybe x1 to xn. These are thetas, but they also, theta 1 up to theta n. Maybe they depend like so on each other in some interesting way. For instance, this could be, what my mobile phone records as location. This is my true location. And of course, since I cannot teleport to the upper level of the lecture theater, it means there is some correlation between the locations. And so even if my sensors on the cell phone tell me I'm here now and in the next second I'm up there, well, we all know that I may have moved in that direction, but I can't have just teleported up there. Okay, so let's use Bayes' rule. So the difference to before, where we have just a single parameter theta that we want to reweight, here we basically want to find want to find a sequence of thetas, and we'll need to sequentially draw from it. So by Bayes' rule, what we have is that p of x n plus 1 and theta n plus 1 given the past is just p of x n plus 1 given the past times p of theta n plus 1 given the past and all the past parameters and the xn plus 1. base rule. So if we sample theta n plus 1, then, okay, that term is perfectly well taken care of, so the only other term we need to worry about is basically we need to reweight things. So we, in other words, have to update the particle weight with, the likelihood that we would have had, that we have for seeing that particular next observation. So what's really going on is the following. This term here is basically how well our set of parameters up to time step n predicts what we're going to see at time step n plus 1. The upper distribution is what, with the benefit of hindsight of having seen the particle, the observation x n plus 1, we now know what theta n plus 1 should look like. So in other words, you first make a prediction, you pay the penalty for doing this, and then you get to revise your view of the world. So that order is important. So it's not like you see a new event and then you say, actually, I already always predicted that this was going to happen, and then, well, you check how well your model fits that, right? So you basically have to be honest and not cheat and not use future information to update your view of the world. So the difference is basically, let's say, based on how well you're doing with the homeworks and all that, you can make some guess about how well you will do with the exam. However, it doesn't make sense to say, well, by the way, here's how well I did with the exam and all of that. So this is now trying now to predict how well you'll do with the exam. I mean, that would be basically cheating by using future information. Okay. Yeah, so this is very, very high level, just explaining a little bit how sequential Monte Carlo can work. So it's basically like an online algorithm. The difference is that you reweight depending on how you do. So let's use that for clustering. So there, while we observe the data in sequence, we have cluster IDs. Let's just use a fully collapsed representation. Then, well, what we do is, for a new observation, we try to see how well our current model fits that new observation. That gives us, P of x n plus 1, given all the past stuff. And then we also draw the cluster ID. So we use the former to get the weighting, we get the latter to our cluster ID. And then if it just so happens that, well, we almost, concentrate, let's say, on maybe 2-3 experts, we resample from these experts to get the uniform distribution again. Maybe, I draw 3 guys from here, 2 guys from there, maybe none from there. And then I keep on moving further. So what this effectively does is it almost gives you something like a phylogenetic tree of joint histories of how your particle filter behaves. Because some particles will die out, some will get refreshed. And by the way, if you're wondering what that piece down here is, does anybody know? Anybody from China would know, right? It's the panda. Yeah. But basically, you get this tree of, and unfortunately I didn't list all the poor animals that died out on this path, but basically you have this dependency graph of where some particles get thrown away and others become resampled, and from there on the history diverges. Okay. So I admit this was like a insanely fast, very, very high level overview of what sequential Monte Carlo can do for you, but at least I hope that you'll have seen a little bit on how multiplicative updates and boosting and game theory and SMC actually all sort of kind of fit together. Yeah, question?
Those particle filters consider the future observations and sampling the current state or not?
To sample, you can, but then you need to make sure that you work out things with the weighting. So you can cheat, but you then have to pay the price on the weights. So that's exactly what happened here, right? So for the sample, so for theta n plus 1, I'm using the future observation. So, once I've seen things, of course, I'll do my very best to update my model based on on that additional evidence. But to find out how well I've done so far, I only am allowed to use any observation, any decisions that I've made up to the point where I had to perform. So you can't just say with hindsight, yeah, I knew how to do that test. Well, if you didn't do it well at the time of the test, well, that's how well you were able to do it. With the benefit of hindsight, you can always do better. Okay. Now, we've missed a lot of stuff, a lot of things that I think are quite important. Neural networks and deep architectures, you should probably at some point read up on that. There's a very nice video lecture on Coursera. Andrew Ng has that. Reinforcement learning, we didn't touch upon that at all. So basically, we only looked at situations where the environment doesn't really do much based on our actions. Well, we touched upon it a little bit in game theory, but not really. Bandits, where that's a little bit less hard than reinforcement learning, but where, unlike for the multiplicative updates so far, you don't really get to see what would have happened had you taken another action. Collaborative filtering, so for instance dealing with Netflix and co, overall recommending things. Scalability, we didn't touch upon that very much at all. Kalman filter, hidden Markov models a bit less so sparse reconstruction. There's a lot of stuff. So in other words, you should take more machine learning classes and read more stuff. And yeah, I mean, that's basically what I want to conclude this with. So please, please, please make sure your slides are up online. So I would appreciate if you could get that done by maybe 5 p.m. tomorrow. Here's why. I want to upload this thing onto my laptop. My network connection at home isn't so amazing, and otherwise I go through my entire network quota by just downloading PDFs from home. So yeah. And yeah, it also takes me some time to compile all that together. Okay. The order in which it appears, if you have any constraints that you cannot present on one day or another and you're scheduled for the wrong day, I need to know ASAP. Don't tell me 5 minutes before the presentation that I get an email, sorry, I can't do it today. That's not cool. Okay. And does anybody have problems with your presentations going up on YouTube? Okay, good. Then they will. Okay, thank you very much for your patience for this class. Do you want to present it?